So today I start with a discussion of the structure which underlies this local to global relation on the Betty side, and which we call the wall crossing structure. And the reference, like the details, can be found in our paper with Maxime in the archive. So two basic examples which one can keep in mind is this family Floer story, which eventually should give us the module. And the second one is this family of Landau-Ginzburg models, which I discussed last time. Now, abstractly, there are kind of a few data which are common in all examples. So I just list the data which are needed for defining the wall crossing structure in general. So it will be, say, a manifold. So there are versions and different generalities. Let's assume that you need a manifold over which the wall crossing structure lives. Local system of free abelian groups called lattices. Local system over n of gamma graded Lie algebras, say over rationals. Now, in general, part of the data is a family of closed cones actually strict convex cones in the vector space generated by the lattice, and they should vary continuously or smoothly on the point of n. Now, this strict cone, this allows us to define for each n a group kind of exponent of Gn if you take only those components, only those gradings which belong to this cone. Now, homomorphism of sheaves of abelian groups or the same, kind of this is abstract, same as local embeddings of n inter dual. And finally, smooth functions. Maybe, okay, so continue here. Just if we consider everything locally, so let's simply identify, let's think that we have just one lattice if we consider everything locally. So we have a lattice, we have a vector space, we have a dual vector space. So this corresponds to some lattice. And so then on here, here we have a collection of walls. So for each gamma and gamma, we have a collection of walls with a set of functionals which vanish on gamma, so countably many walls. And so then this local embedding gives us a collection of walls on N. So, okay. And then the last piece of data is a collection of homomorphisms, well, how to say it, maps x, gx to gy, where x and y belong to N minus the union of all walls. So if N in the simplest case, which is already interesting actually, it's related to last time story, we can take N to be equal just gamma R dual. So then we have a vector space with a collection of walls, can be finitely many or countably many. And if you take two, let's call them irrational points, because they are outside of countably many walls, two generic points, then we have an element with corresponding group. Yeah, and these elements should satisfy the cycle condition, or gxz. So if we have 3 points, then gxy product with gyz should be equal to gxz. Okay, so example related to the last time discussion of a family of Landau-Ginzburg models. So we have N to be product. This is an open part over which the number of critical values do not change. So gamma u, so u here, gamma uh, in fact it does not depend. This is a set of don't remember how I denoted critical values. View. It's a map which sends a collection points to their sum. So yes. So what's wrong? Okay. But is it better? So okay. All right. Now. Yeah, the Lie algebra actually is just the algebra of endomorphism. It's a matrix algebra, if you like. It's an algebra of endomorphisms of these cohomology groups. Betty, local Zi of U, and the angle is argument of minus h, something like this. Yeah. Maybe tensor. So, yeah, since it has to be a Lie algebra over rationals. So this. So it's finite dimensional. And so the central charge okay, first walls can be described. Oh no, let's define the central charge. So it's constant.
What is what's called y on the previous floor?
Okay, y will be given by the imaginary part of the central charge. So then it's y. I mean, you know, x is the real part of something if it's not a scheme. Y is imaginary part of something. Z is x plus square root of y. So I define z, then take its imaginary part. It's a homomorphism from this lattice. So this lattice is generated, of course, by vectors where everything we have 0, 1 is 1, so this is sum, so sum must be equal to 0, so say I minus 1j, something like this. Yeah. So then this maps Eij to Zi of U. So this is a collection Zi of U of critical values minus Zj of U and over H. Like that. Now walls. It's a collection of pairs where okay, so always capital Y is imaginary part of the central charge. Okay, this is called central charge. Now it's a collection of U and Y. There exists some non-zero whatever gamma and gamma UH minus 0 such that ZU, technically it should be Z, okay. This does not depend on H, as you see. So let me denote it by gamma U, so then, so. Yes. Okay. Yeah. ZUH over gamma is a positive real number. Yeah. So it's a codimension one event, and so these walls belong to this set. And so in order to define, so here we do not have a cones, everything is finite dimensional. So then what is left is to, I mean, in order to define the wall crossing structure, we need, so since a group is just a group corresponding to this Lie algebra with Lie bracket, which is a commutator. So then the wall crossing structure is defined, is determined by a collection of elements AQH, which belong to the sum UH gamma, graded components, overall gamma, whatever is enough to maybe, okay, maybe it was better to write this as ZU divided by H. Okay, but anyway. All right. And the transitivity condition, cycle condition, means that if we take a small loop, sigma, so we have here, this is a loop in our N, then the product, say in the clockwise direction of the element A, UI, HI, overall intersection, so this belongs to the intersection, okay, sigma intersection with walls. So this product is equal to 1. So it's kind of triviality of the monodromy condition. So, and last time actually I explained these automorphisms. It's called TIJ, something like that. So then this condition, the cycle condition, or this triviality of the monodromy condition, it's exactly, so it's a remark. Let's call this, same as this, is equivalent to, in this case, to this Chicotti-Waffa or Picard-Lefschetz, as Misha called it, wall crossing formulas, which I wrote last time. Okay, so which is, so I wrote it kind of explicitly, but it's equivalent to the identity for the product of three matrices is equal to the product of other three matrices on the left-hand side of the wall, on the right-hand side of the wall, what we did last time. So then Lie algebra is basically GLN, but the wall crossing formula, generically it involves just 3 points, I, J, and K, and so this is the identity in GL3. So it's 3 by 3 matrix. All right. And now what next? There is a similar story with kind of a generalization. So it's another remark. So there exists a generalization of this story. Which means that family Landau-Ginzburg models, if you like, to the family of manifolds ended with closed one forms, which are not necessarily exact. But again, the condition is that they are obtained by restriction of some global closed one form in the total space of the family. So the story is very much similar to this one. There is a kind of a new feature in terms of the wall crossing formula. So, so just some changes. Then now we have kind of a zeros of one form instead of just critical values. And here the lattice, it's this kernel lattice, which is basically, it's a root system for the corresponding Lie algebra, plus some other lattice, which is, so lattice, so I would like just to present it this way, lattice of relative integer relative one homology. Integer. Okay, maybe let me write it. Just denote it somehow. I don't know. Gamma H. And this is hold on. You mean that there are also closed loops? Yeah, okay, yeah. Okay. So zeros. No. Yeah. So I have some kind of zeros of the one form, and I consider path as gamma between different connected components. So if I have such a path, I can integrate one form, and this gives a central charge. And again, I can rescale it by, if I like, I can rescale everything by a complex number. So, and the difference now is in the Lie algebra as well, because here it was just a finite dimensional vector space for each u and h, and here this old whatever G, this new Lie algebra, it should be the old one tensored with a group. Now it's okay. With a group algebra of this lattice, which is just algebra of Laurent polynomials. So then now it's infinite dimensional. Okay, so instead of discussing this finite dimensional story, I consider an example in infinite dimensions because it will demonstrate some new phenomena. So again, this Chicote-Waffa, which kind of this Picard-Lefschetz was originally attributed to Chicote-Waffa, it's known in physics as 2D wall crossing formulas because they describe the change in the number of solitons in some massive two-dimensional quantum field theory. Now, when we go to the case of closed one forms, especially in infinite dimensions, we'll have new kind of wall crossing formulas which are known as 4D and mixture of these two, 2D, 4D. So there will be new walls and new wall crossing formulas. So the basic example which we should keep in mind, it's an example of infinite dimensional space of C infinity paths between two holomorphic Lagrangian submanifolds. So I start with a complex symplectic manifold. These are Lagrangian submanifolds. Actually, maybe submanifolds is sort of too strong condition. Maybe it's enough to have them just Lagrangian subsets allowed to singularities. So now define the space of C infinity paths well, they're continuous in the closure, otherwise smooth, with the endpoint some standard object in the Floer theory with one difference that the boundary Lagrangians are holomorphic. So, and this is an infinite dimensional, but it's a complex manifold. So it carries a holomorphic, so one form, which is basically defined can define roughly. So, and the tangent space is a vector field along the path which is tangent to Lagrangians at the endpoint. So then you can integrate it and check that it's closed. Or kind of a little bit more pedantically, you can you have two projections to X and okay. Then we define alpha as integral, and now there is an evaluation map. So evaluation map of just the value of phi of t. So then this is a closed one form. But in general, it is not exact. But I consider first the case when it is exact. And for that, we impose a condition. So first assume that M is exact, which means that, and L0, L1 are exact as well, which means that if I restrict this to Li, it's differential of some function dfi. So then one form is also exact, and this function can be written explicitly. And corrected with some boundary conditions. Something like this. Now, zeros of the closed one form, the same as critical values of f. And so it's easy to see that it's just the intersection. Okay. Which I will identify. Okay. Constant maps. So anyway, this is all right. So we have this in infinite dimensions. We have the data which are similar to what we discussed in the previous lecture, with only difference that now we do not have neither de Rham nor Betti cohomology theories. So then there are two ways, either to kind of invent these theories or use one of the ad hoc proposed candidates, or to use the approach from local to global, which means basically try to construct the wall crossing structure, if you like, starting with some data, and I mean construct it inductively, starting with some local data in the critical locus. So what we will do, we impose some extra assumptions on the data, and then, you know, like we assume that everything is algebraic, and we use the sheaf of vanishing cycles of the arising functions on finite dimensional varieties as a replacement for the topological construction. So which means that, so let's assume, So assume that this critical set is a union of, is a finite union. Oh, it's not good notation. So which letter is good? So, okay. Z. It's a finite union. These are connected components. And these are finite dimensional algebraic. Okay, these are finite dimensional algebraic varieties. Let's call this union Z, so it's still finite dimensional manifold. And let's assume that there exists some, how to call it, epsilon neighborhood of this set in infinite dimensional space. And the projection it to something finite dimensional. I don't know. This finite dimensional manifold. Or maybe I should denote it by U in agreement with what was before. Let's call it pi. And assume that every fiber has only one, so kind of, if I restrict F to the fiber, to every fiber, maybe I should denote it actually by U0, has only one critical, Morse critical point. There's only one critical point, which is Morse. No, I think it's not enough. No, I think near every, okay. No, I think I need it to be true in the neighborhood of so one critical point. I think it should hold for the neighborhood, for sufficiently small neighborhood of. No, this is a sort of a general story, but this intersection doesn't have. Well, first of all, intersection doesn't have to be transversal. It's kind of okay. So there's only one critical point. How to say it? So suppose I restrict. Okay, if I restrict F to a connected component, so since it's connected and it's critical, so it has one critical value, say Z alpha. So I want this to be true locally. So if I want this to be true locally in the neighborhood of the. Okay, yeah. Okay, yeah, it has one critical point, one Morse critical point for all p minus 1 of u close to the alpha, like this. So I have this smooth component which is finite dimensional. And then I consider a neighborhood in the space of all paths. I don't know, you explained. Not. Yeah, good. So then but for the rest, this is the intersection of two Lagrangians, which is kind of compact. Maybe even compact, but not necessarily finite. And you consider its neighborhood in the infinite dimensional space. So if you assume that here, so it's projected to something finite dimensional, and here there is only one Morse critical point with one critical value, and so we can define the new function f bar. Can define new holomorphic function which is this critical value f bar of u. It's the only, okay, it's called the alpha of u. So then morally you can think that some function plus a quadratic form in infinitely many variables in a transversal direction. Okay, and now after these assumptions we simply define, so define the local Betti cohomology, whatever argument of H as shifted by the dimension. Yeah, anyway, but it should be shift. And here we need more space. So this is a sheaf of vanishing cycles. Like the realistic examples which can be of interest is, for example, a complexified or Chern-Simons or even holomorphic Chern-Simons. Unfortunately, the corresponding closed one form is not globally exact. But nevertheless, the idea is the same. So you look at the set of critical, a set of zeros of the corresponding one form, like imagine that it's exact, nevertheless. And so then there is some, it's like space of flat connections, complex valued. And you can try to define some, in the end, some vector bundle by looking, by splitting this Chern-Simons functional into the sum of some finite dimensional function and the quadratic form in infinitely many variables. Something like this. Okay, this is one thing. It's the replacement of the local Betti cohomology. And secondly, this matrix Tij, which appear when we cross the wall, is a matrix with matrix coefficients which is, it's what is natural to do by analogy with what we discussed, which is a number of gradient lines between two connected components. Well, better to say between 2 points in this. So we should take some point here and point here, because these components do not have to be simply connected. Yeah, so then the gradient line, it has its relative homology class. If the component is not simply connected, then the number depends. Yeah, you are right. In the fixed, yeah, okay. No, it's not. No. It's separator. It's a matrix. You see, the matrix. Matrix is a map. Okay, and linear map. Yeah, I need to choose. Yeah. In the Morse case, yeah, I would like to think that I can choose a basis of symbols by considering gradient lines. I think I can do this. I can. Yes, Morse means all critical points are Morse. Yeah, that's the main example which I considered last time. Yeah. No, I did. No, I did not assume it secretly. I wrote it on the blackboard.
No, it's Morse function of fibers.
Ah, you mean that this F? Okay. Okay. In order to kind of wrap up this discussion, assume that it's Morse, which okay. Assume it is also Morse. Then I can choose a basis. Yeah, but otherwise, okay. So if it's not Morse, then I will have a linear operator. Between two spaces. Okay, if it's not Morse, then I simply consider for any relative homology class with joint 2 points in Z alpha I and Z alpha j, I have the corresponding linear operator between these finite dimensional vector spaces. Yeah. So, okay, if not, okay, it's comment. But if it's Morse, it's nice because you can read Witten's paper where he considered it symbols business. If F is not Morse, you have, should I denote it, T gamma ij. Yeah, yes, but you do have a you do have a perverse sheaf because it's Landau-Ginzburg model. So there's Betty, and here you have local Z alpha j, and here we take Z alpha j, and this sheaf of vanishing cycles, and to the similar story with Z alpha j. So So you have, and gamma ij is a relative homology class. Z alpha I, Z alpha j, and this is whatever class of this. All right. Now, in order to make all this kind of well-defined, we need to impose some conditions, of course, in order to speak about gradient lines. So we should assume that M is scalar. Now, in order to make this count well-defined, we need to assume that the corresponding nonlinear operators in B, they are elliptic. So, ellipticity in count B. And I think it, well, without this assumption, B doesn't make any sense. So what is, you have to prove it. I don't know how it's, you need, okay. It's logic, yeah. Assumption which you assume something, just impose an additional condition. You have to prove. This is an assumption, all right. You have to assume, you have to prove, yeah. Now, what else? The remark, in order the sheaf of vanishing cycles to be well defined, you need to choose an orientation data. You see, it's three different words: assume, prove, and choose. Choose orientation data to have the sheaf of vanishing cycles to be well defined. Because the sheaf of vanishing cycles, it depends on this extra quadratic form. So in the this is actually quite general, but in the case, yeah. Now, if we assume that this is Keller, then similarly to this closed one form, we can define the Keller form on the space of paths, and so then we can speak about gradient lines. As for ellipticity, so I don't know. Do you know how to check it? Yeah, I understand. Write equations and prove that it's elliptic, but I don't know. Yeah, okay. Like Kapustin-Witten equation for the Chern-Simons. So then you have to prove something, yes, which is not trivial. Now, as for orientation data, I really don't want to discuss it in detail because it's a long story. It has its categorical counterpart. Categorical meaning, I mean, in the case of sheaf of vanishing cycles, it's obvious. You can add the quadratic form, and you should fix the corresponding orientation line bundle for this quadratic form. But it has many incarnations for categorical meaning in the theory of DT invariants. Look at our paper, which means basically in the framework of categories, it's a choice of the quadratic form of the determinant of the extension bundle from an object to itself, some line bundle, In Fukaya, it's choice of the pin structure of a Lagrangian. So in deformation quantization, it's choice of quadratic root of the canonical class. So anyway, it's kind of a part of the data of the story everywhere. In this particular case of the space of paths, we need to choose a quadratic root of the canonical class of each Li and probably of M. M is automatic, yeah, just of Li. Yeah. All right. Now, this is an infinite dimensional story, and if you forget about many justification questions, then you have the same story as in finite dimensions. You have this cohomology, Betti cohomology, which depends on this Planck constant, depends on the point Q. And now we have walls. So we have new type of walls in this story. So remember that when we discussed this Riemann-Hilbert story from the Foucault point of view, so we had Stokes race on which something happened. We corrected some naive definitions, and this something was the existence of a pseudo-holomorphic disk with the boundary. Okay, let's denote it somehow. Let it be L0. And this is L1. So new disks, in the Floer, in the Fukaya category, disks which used in the definition of Floer differential. So this what I call today 2D walls and 2D or Chicotti-Waffa wall crossing formulas when we cross those walls. That was our story for the previous 2 lectures where we have this Tij, everything was written explicitly. Now, in general, we can have a new type wall crossing formulas which and walls which arise not only from something which is kind of very well known in Floer theory, like existence of these bigons, in this case 2 gons, but also we can have an additional disk with a boundary, say in this case, for example, like imagine an L0 on the spectral curve. In the case of, if it's something more subtle like holomorphic Chern-Simons, where the gradient trajectories, say, they correspond to, they live in 7 dimensions, it's kind of a G2 holonomy stuff. So then this bubbling means appearing of new Lagrangians. But in the case of pair of holomorphic Lagrangian submanifolds, we can have these disks, and so our Stokes automorphisms, they should take this into account. So then we have more complicated wall crossing formulas, which are 2D, 4D wall crossing formulas in terminology of physicists. Let me see how much time do I have. Yeah, so that's okay. So I'm just thinking. So this does not happen in the case when, in the exact case which we considered previously. Here I impose a condition, that exactness condition, which imply that my form is exact. So, but in general, it can happen that we have this these disks with a boundary on either of the Lagrangians, which means that from the point of view of the corresponding Morse theory, so when, or Floer theory in this case, this means that there are new components in the space of gradient lines. So in Morse theory, the fact that d square is equal to 0 is related to the fact that for appropriately chosen critical points, the only thing which can happen with the gradient trajectory is to go to some additional kind of point, critical point of the wrong Morse index. But and then this means that the boundary, the moduli space of gradient lines between two Morse critical points with the index different by 1, it's a product of two moduli spaces for moduli space of this and moduli space of this. And so it's a standard proof that d square is equal to 0, but if we have new components, so then it makes life more complicated. And these 2D, 4D wall crossing formulas, they are known. So this Chicotti-Waffa or 2D wall crossing formulas, or Picard-Lefschetz, as Misha called them. And this is a mixture of two. And I erase it. So for 2D wall crossing formulas, our Lie algebra, as I told you, it's essentially the Lie algebra GLN. So, and when we cross a wall of real codimension 1, when 3 points, like in example 3 points collide, then we have this simple Chicotti-Waffa story. So here we have GLN tensored with Laurent polynomials. Remember, we have this group algebra of the lattice of relative one homology. So then in this case, what we constructed in the end was a vector bundle over C star of H, have some vector bundle. So here we still have this C star, but also we have an auxiliary torus. And so what we are doing, we're constructing vector bundle over this. Okay. And probably last thing which I will explain. Let me think. Okay, maybe last thing. A year ago, Maxim gave a nice lecture course on exponential integral at IHS, and he presented an example of constructing of kind of a D module from this wall crossing data. So I borrow this example because it will make a connection with Riemann-Hilbert. So it sort of unites all the topics except maybe of this 2D 4D wall crossing. Okay, so this example. So the details lecture HS. I think it's online. 14, 15, I don't remember the year. So, okay, anyway, one of the two. Maybe it was last year, maybe it was 2 years ago. Last year, okay. Then it's 2015. So now we have a curve. So again, it's back to one-dimensional case, which is a line. So this is a holomorphic symplectic manifold, which is C cross C. Now, it's an algebraic story, so we can set the Planck constant to be equal to 1. And L0 will be kind of is a 4-to-1 ramified cover of the base of C. So it's explicitly given by the map. So it's something like this. Let's say it's QP, and I don't know to write it down. Yeah, something like this. Okay. So then it is exact. So with a function which is x cubed over 3, 2/3. Yeah, I think this is true. Okay, hold on. PDQ restricted to 0 x squared plus 4x5 dx. Yeah, I think this is So there are 3 critical values Q1, Q2, and Q3 for the projection of L0. L0. So again, it's kind of 1 plus 4x cubed. It comes from the solution to this equation. So all they are Morse. And so they are vertices which belong to the corresponding walls. It's a story, in a sense, it's kind of similar to what we discussed last time with Landau-Ginzburg. So these are equations yeah. 3 is a positive number. And the second one. So similarly to what we saw last time, this Landau-Ginzburg story when 2 points collide, go to the discriminant, forming an A2 singularity. Here we have kind of 3 rays with the angle of 120 degrees coming out of this critical values. And again, similarly to what we saw last time, in order to construct the wall crossing structure, we assign, since they are Morse, we assign to them number Nij equal to 1. And then there is a scattering process when these walls meet. So we use this Chicotti-Waffa wall crossing formulas to produce new numbers. So, and if our curve was compact, I think this was it. We would have the wall crossing. This will give us a connection, the D module. But since it's non-compact, so we need to take into account the behavior at infinity. And this will give us a different type of walls. So now we should look, so new walls at infinity, because we should look at the exponent of the real part of the corresponding functions. It's multi-valued function coming new walls, or if you'd like, Stokes data at infinity coming from the filtration, or it corresponds to the filtration given by real parts of the code. So then have this sort of very explicitly given picture, which in the end can be interpreted as a construction of irregular D module. So I think in order to, so maybe I should rather kind of, so there are two possibilities. Yeah, the easiest one is just to stop now and to save some time. Otherwise, I can discuss this Chern-Simons, but I think 15 minutes is not enough.
It's up to you.
Okay. So maybe I should better stop now.